Hey guys, we're going to talk about sigma notation today. We know that a series is the sum of terms of a sequence. When it can be written in a form called sigma notation. Okay, the symbol sigma, this is the 18th letter of the Greek alphabet. And it looks something like this. So you would see sigma, you would see n equals 1 up to 5 of 4 and minus 3. So we have a couple of things here. The first thing we have is this n. This n, it's called the index. It's called the index. Sorry, guys. Called the index, and it represents a variable. And it's going to be integer, which will be integer. It's generally a counter, so either it starts at 0 or 1, but it could start at any number. The 1 here, that's known as the lower limit. The 5 here, this is going to be the upper limit. And the 4 and minus 3, this is the general term. It's the same general term that we found from the arithmetic and geometric sequences. And so consecutive n values are going to be plugged into the general term and then added together. And so it simply goes like this. So, so it would be, you'd start with the first number 1. So it would be 4 times 1 minus 3. And then what comes after 1? It's 2 plus 4 times 2 minus 3. And then after 2, it's 3. 4 times 3 minus 3. After 3, it's 4. 4. And then after 4, it's 5. And now we've reached our upper limit. And then either you add these together. The idea is that you're going to put this in like your computer. Your computer's going to, the tech is going to do it for you, or a computer is going to do it. And we can see that you start at 1, like up to 1 million, and the computer does it like that. And then you figure it out. Let's see, 1 plus 5 plus 9 plus 13 plus 17. What do we have? 30, 45. So the sum is 45. We could also take a look at something called an infinite series. An infinite series has an upper limit of infinity, and it's written as, for example, sigma notation of n equals 1 to infinity of, let's see, like 1/2 to the n. Now, we've seen this before. We're going to be talking about this, or we've spoken about it with an infinite geometric series. So it's like 1/2 plus 1/4 plus 1/8 ad infinitum. And we know the answer is, who knows the answer? Well, either we've done it and we know the answer is 1, or we will do it and the answer is 1. And try these on your own. So let's see, I'm going to erase this. And so here's two examples for you to do, just to write it out. Here's the first one, sigma, the sum from 2 to, from 2 to 4 of 3 to the k, and try sigma from m equals 0 to 3 of 1 over m plus 1. So try these. Okay, we're back. And so you know that this is 3 squared plus 3 to the third plus 3 to the fourth. So you would use your GDC for this. It's pretty big. So what is it? It's 9. 81 plus 9 is 90. 90 plus 27 is 117. And then here we have 1 over 1 plus 1 plus 1 over, 0 plus 1 plus 1 plus 1 plus 1 over 2 plus 1, which is equal to 1 plus a half plus a third. What does that equal? What does that equal? Let's see, 3 over 2 plus 1/3. And so what is this? It's 11 over 6. Now, just a quick thing. These are known as dummy variables. This n, k, m, these are dummy variables. And so they can be transformed. They're just letters. You can use any letter you want. The last two things. The question is, how do we take? We know how like a sigma notation can generate a series. The question is, if I give you a series, can you turn it back into sigma notation? And the answer is very easy. We're going to look at we're just going to look at examples with arithmetic sequences and geometric sequences. If you see like these two, you kind of you'll do it by inspection. You can do it by inspection to construct the sigma notation, but sometimes you want to figure it out. Sometimes you notice it's arithmetic, geometric. So let's take the first example. So going from a series to sigma notation. So for example, I say 1 plus 5 plus 9 plus 13 plus 17 plus 21 plus 25. The question, I don't want to write all that out. I just want to tell a computer to do that. Can I, how do I get it in my GDC, my computer? Well, easy. First, you know it's an arithmetic series. You immediately identify the fact that the common difference is 4. So that means I can write the general term. The general term is u of n is equal to 1 plus n minus 1 times 4. So the general term, which we know is going in our sigma, is, let's see, 4n minus 3. So I have the general term. I need to know what my lower and my upper limits are. Well, we're always going to start with 1. The question is, how many terms are there? The upper limit is the number of terms. Well, it's clear. 1, 2, 3, 4, 5, 6, 7. Either you can tell us 7 or you can figure out how many terms there are. So we know that n equals 7. Therefore, we say that sigma from n equals 1 to 7, of 4n minus 3. And this sigma notation represents this series. Let's take a look at a geometric one. How about we look at 3 plus 6 plus 12 plus 24 plus 48. Right? So the question is how do we write this in sigma notation so we can easily get it into our GDC? Well, once again, you immediately recognize that this is a geometric series, and the ratio is 2. So the general term of the geometric series is u of n is equal to 3 times 2 to the n minus 1. Right? Next, so I have my general term. I know what's going over here. The question is, what's my upper limit? My lower limit is going to be 1, and my upper limit is the number of terms. Well, I can clearly see there's 5 terms here. So the n equals 5 Therefore, I can write sigma notation, n equals 1 up to 5, of 3 times 2 to the n minus 1. If you think about this, the first term, 1 minus 1, 2 to the 0, that leaves me with my 3. So it's like my initial value. It's interesting, it pulls it back. You could technically write, or, you could start at 0, right, and go up to 4 of 3 times 2 to the n. That's your call. But you should recognize that 0 is the initial, it's the first thing you're looking at. I get a little weird about this, but whatever. And another thing we can do is, we can pull out, and this is a little advanced, we start with 1 to 5, but I can pull out, because it's 2 to the n minus 1, that was 2 to the n divided by 2. So I could technically write it as 3/2 times 2 to the n. Good. Just some old school stuff now. You can stop watching the video, or you can watch just for a little old school. Some things. Old school. So, sigma notation, let's let C be a constant. Like 2, 8, 1,000. So, the summation of a constant times the general rule is equal to, I can pull the C out, like the distributive property, or factoring. Also, so let's take a look at that. So for example, if I say 15 plus 30 plus 45 plus 60. Now, excuse me. We know with technology this is not a big deal anymore. You can quickly create sigma notation, but you have to think, like, you look at these rules in the book, you're thinking, wait a minute, if it was 1987 or 1952, they had to make their life a little easier. So we know, just by inspection, that we have 4 terms. I apologize. We have 4 terms, and we clearly see it's like 15n. So the first term is 15, 30, 45, 60. Well, let's say I factored out that 15. 1 plus 2 plus 3 plus 4. I know that I have 15 sigma n minus 1 to the 4 of n. And you can see, once again, you can pull a constant out. You can see how easy this would make your life. Let's say you only have like a scientific calculator. Well, I know to add 1 plus 2 plus 3 plus 4. That's easy. That's 10, right? 10 times 15 is 150. But this might be a little more cumbersome. The last thing I want to talk about is simply this last rule, which is the summation of C, and that's simply NC. What's going on here? Well, let's just do an example. How about we take sigma notation from n equals 1 up to, well, let's start at k and go up to n. Well, let's go up to like 8, 5 to make our life easier, with a constant like 3. All right? Well, technically there's nothing really here, so I'm just adding 3 5 times. Right? Because it's a counter. What's the first term? 3. What's the second term? 3. 4, 3. 3, 3. So it's 3 times 5, which is 15. So that's the 2 rules. Once again, technology makes this much easier, but these are old school rules. Thank you.